Dijkstra's algorithm, conceived by computer scientist Edsger Dijkstra in 1956 and published in 1959, is a graph search algorithm that solves the single-source shortest path problem for a graph with non-negative edge path costs, producing a shortest path tree. This algorithm is often used in routing and as a subroutine in other graph algorithms. For a given source vertex in the graph, the algorithm finds the path with lowest cost between that vertex and every other vertex. It can also be used for finding costs of shortest paths from a single vertex to a single destination vertex by stopping the algorithm once the shortest path to the destination vertex has been determined. For example, if the vertices of the graph represent cities and edge path costs represent driving distances between pairs of cities connected by a direct road, Dijkstra's algorithm can be used to find the shortest route between one city and all other cities. As a result, the shortest path algorithm is widely used in network routing protocols, most notably IS-IS and OSPF. Dijkstra's original algorithm does not use a minute priority queue and runs in time. The idea of this algorithm is also given in the implementation based on a minute priority queue implemented by a Fibonacci heap and running in is due to. This is asymptotically the fastest known single-source shortest path algorithm for arbitrary directed graphs with unbounded non-negative weights. Algorithm. Let the node at which we are starting be called the initial node. Let the distance of node y be the distance from the initial node to y. Dijkstra's algorithm will assign some initial distance values and will try to improve them step by step. Assign to every node a tentative distance value, set it to 0 for our initial node and to infinity for all other nodes. Mark all nodes unvisited. Set the initial node as current. Create a set of the unvisited nodes called the unvisited set consisting of all the nodes. For the current node, consider all of its unvisited neighbors and calculate their tentative distances. Compare the newly calculated tentative distance to the current assigned value and assign the smaller one. For example, if the current node A is marked with a distance of 6, and the edge connecting it with a neighbor B has length 2, then the distance to B will be 6 plus 2 equals 8. If B was previously marked with a distance greater than 8, then change it to 8. Otherwise, keep the current value. When we are done considering all of the neighbors of the current node, mark the current node as visited and remove it from the unvisited set. A visited node will never be checked again. If the destination node has been marked visited or if the smallest tentative distance among the nodes in the unvisited set is infinity, then stop. The algorithm has finished. Select the unvisited node that is marked with the smallest tentative distance, and set it as the new current node. Then go back to step 3. Description. Note, for ease of understanding, this discussion uses the terms intersection, road and map. However, in formal notation these terms are vertex, edge and graph, respectively. Suppose you would like to find the shortest path between two intersections on a city map, a starting point and a destination. The order is conceptually simple. To start, mark the distance to every intersection on the map with infinity. This is done not to imply there is an infinite distance, but to note that intersection has not yet been visited. Some variants of this method simply leave the intersection unlabeled. Now, at each iteration, select a current intersection. For the first iteration, the current intersection will be the starting point and the distance to it will be 0. For subsequent iterations, the current intersection will be the closest unvisited intersection to the starting point. This will be easy to find. From the current intersection, update the distance to every unvisited intersection that is directly connected to it. This is done by determining the sum of the distance between an unvisited intersection and the value of the current intersection, and relabeling the unvisited intersection with this value if it is less than its current value. In effect, the intersection is relabeled if the path to it through the current intersection is shorter than the previously known paths. To facilitate shortest path identification, in pencil, mark the road with an arrow pointing to the relabeled intersection if you relabel it, and erase all others pointing to it. After you have updated the distances to each neighboring intersection, mark the current intersection as visited and select the unvisited intersection with lowest distance €. or the lowest lobular as the current intersection. Nodes marked as visited are labeled with the shortest path from the starting point to it and will not be revisited or returned to. Continue this process of updating the neighboring intersections with the shortest distances, then marking the current intersection as visited and moving on to the closest unvisited intersection until you have marked the destination as visited. Once you have marked the destination as visited, you have determined the shortest path to it, from the starting point, and can trace your way back, following the arrows in reverse. Of note is the fact that this algorithm makes no attempt at direct exploration towards the destination as one might expect. Rather, the sole consideration in determining the next current intersection is its distance from the starting point. This algorithm, therefore, expands outward from the starting point, interactively considering every node that is closer in terms of shortest path distance until it reaches the destination. When understood in this way, it is clear how the algorithm necessarily finds the shortest path. However, it may also reveal one of the algorithm's weaknesses, its relative slowness in some topologies. Pseudocode: in the following algorithm, the codeway equals vertex in Q with mindest, U, searches for the vertex U in the vertex set Q that has the least dist, U, value. Length, U, B, returns the length of the edge joining the two neighbor nodes U and B. The variable alt on line 17 is the length of the path from the root node to the neighbor node V if it were to go through U. If this path is shorter than the current shortest path recorded for V, that current path is replaced with this alt path. The previous array is populated with a pointer to the next hop node on the source graph to get the shortest route to the source. 1 function Dijkstra, graph, source, 2 dist, source equals 0 distance from source to source, 3 for each vertex V in graph, initializations, 4 if V a permil source, 5 dist, V equals infinity unknown distance function from source to V, 6 previous, V equals undefined previous node and optimal path from source, 7 end if, 8 add V to Q all nodes initially in Q, 9 end for, 10, 11 while Q is not empty, the main loop, 12 U, equals vertex in Q with mindest, U source node in first case, 13 remove U from Q, 14. 15 for each neighbor V of U, where V has not yet been removed from Q, 16 alt, equals dist, U, plus length, U, B, 17 if alt dist, B, a shorter path to V has been found, 18 dist, V equals alt, 19 previous, V equals U, 20 end if, 21 end for, 22 end while, 23 return dist, previous, 24 end function. If we are only interested in a shortest path between vertices source and target, we can terminate the search at line 13 if U equals target. Now we can read the shortest path from source to target by reverse iteration. 1s equals empty sequence, 2u equals target, 3 while previous, u, is defined, construct the shortest path with a stack s, 4 insert u at the beginning of s push the vertex into the stack, 5u, equals previous, you traverse from target to source, 6 end while. Now sequence S is the list of vertices constituting one of the shortest paths from source to target, or the empty sequence if no path exists. A more general problem would be to find all the shortest paths between source and target. Then instead of storing only a single node in each entry of previous, we would store all nodes satisfying the relaxation condition. For example, if both are in source connect to target and both of them lie on different shortest paths through target, then we would add both are in source to previous, target. When the algorithm completes, previous data structure will actually describe a graph that is a subset of the original graph with some edges removed. Its key property will be that if the algorithm was run with some starting node, then every path from that node to any other node in the new graph will be the shortest path between those nodes in the original graph, and all paths of that length from the original graph will be present in the new graph. Then to actually find all these shortest paths between two given nodes, we would use a path-finding algorithm on the new graph, such as depth-first search. Using a priority queue, a minute priority queue is an abstract data structure that provides 3 basic operations: add with priority, decrease priority and extract min. As mentioned earlier, Using such a data structure can lead to faster computing times than using a basic queue. Notably, Fibonacci heap or Brodel queue offer optimal implementations for those three operations. As the algorithm is slightly different, we mention it here, in pseudocode as well. 1 function Dijkstra, graph, source, 2 dist, source equals 0 initializations, 3 for each vertex v in graph, 4 if v a permil source, 5 dist, v, equals infinity unknown distance from source to v, 6 previous, v, equals undefined predecessor of v, 7 end if, 8 pq add with priority, v, dist, v, 9 end for, October 11th 12 while pq is not empty, the main loop, 13 u, equals pq extract min remove and return best vertex, 14 for each neighbor v of u, where v has not yet been removed from pq. 15 alt equals dist, u, plus length, u, v, 16 if alt dist, v, 17 dist, v, equals alt, 18 previous, v, equals u, 19 pq decrease priority, v, alt, 20 end if, 21 end for, 22 end while, 23 return previous. It should be noted that other data structures can be used to achieve even faster computing times in practice. Running time, an upper bound of the running time of Dijkstra's algorithm on a graph with edges and vertices can be expressed as a function of and using big O notation. For any implementation of vertex set the running time is in, where and are times needed to perform decrease key and extract minimum operations in set, respectively. The simplest implementation of the Dijkstra's algorithm stores vertices of set in an ordinary linked list or array, and extract minimum from is simply a linear search through all vertices in. In this case, the running time is. For sparse graphs, that is, graphs with far fewer than edges, Dijkstra's algorithm can be implemented more efficiently by storing the graph in the form of adjacency lists and using a self-balancing binary search tree, binary heap, pairing heap, or Fibonacci heap as a priority queue to implement extracting minimum efficiently. With a self-balancing binary search tree or binary heap, the algorithm requires time. To avoid lookup and decrease key step on a vanilla binary heap, it is necessary to maintain a supplementary index mapping each vertex to the heap's index, making it take only time instead. The Fibonacci heap improves this too. Note that for directed acyclic graphs, it is possible to find shortest paths from a given starting vertex in linear time, by processing the vertices in a topological order, and calculating the path length for each vertex to be the minimum length obtained via any of its incoming edges. Related problems and algorithms, the functionality of Dijkstra's original algorithm can be extended with a variety of modifications. For example, sometimes it is desirable to present solutions which are less than mathematically optimal. To obtain a ranked list of less than optimal solutions, the optimal solution is first calculated. A single edge appearing in the optimal solution is removed from the graph, and the optimum solution to this new graph is calculated. Each edge of the original solution is suppressed in turn and a new shortest path calculated. The secondary solutions are then ranked and presented after the first optimal solution. Dijkstra's algorithm is usually the working principle behind linked state routing protocols, OSPF and IS-IS being the most common ones. Unlike Dijkstra's algorithm, the Bellman-Euroford algorithm can be used on graphs with negative edge weights, as long as the graph contains no negative cycle reachable from the source vertex S. The presence of such cycles means there is no shortest path, since the total weight becomes lower each time the cycle is traversed. It is possible to adapt Dijkstra's algorithm to handle negative weight edges by combining it with the Bellman-Ford algorithm. Such an algorithm is called Johnson's algorithm. The A algorithm is a generalization of Dijkstra's algorithm that cuts down on the size of the subgraph that must be explored, if additional information is available that provides a lower bound on the distance to the target. This approach can be viewed from the perspective of linear programming. There is a natural linear program for computing shortest paths, and solutions to its dual linear program are feasible if and only if they form a consistent heuristic. This feasible dual/consistent heuristic defines a non-negative reduced costs, and A is essentially running Dijkstra's algorithm with these reduced costs. If the dual satisfies the weaker condition of admissibility, then A is instead more akin to the Bellmani-Ford algorithm. The process that underlies Dijkstra's algorithm is similar to the greedy process used in Prim's algorithm. Prim's purpose is to find a minimum spanning tree that connects all nodes in the graph. Dijkstra is concerned with only two nodes. Prim's does not evaluate the total weight of the path from the starting node, only the individual path. Breadth-first search can be viewed as a special case of Dijkstra's algorithm on unweighted graphs, where the priority queue degenerates into a FIFO queue. Fast-marching method can be viewed as a continuous version of Dijkstra's algorithm which computes the geodesic distance on a triangle mesh. Dynamic programming perspective. From a dynamic programming point of view, Dijkstra's algorithm is a successive approximation scheme that solves the dynamic programming functional equation for the shortest path problem by the reaching method. In fact, Dijkstra's explanation of the logic behind the algorithm, namely, Problem 2. Find the path of minimum total length between two given nodes and. We use the fact that, if is a node on the minimal path from 2, knowledge of the latter implies the knowledge of the minimal path from 2. Is a paraphrasing of Bellman's famous principle of optimality in the context of the shortest path problem. See also. A search algorithm, Bellmani-Ford algorithm, Euclidean shortest path, flood-fill, Floyd-Walshall algorithm, Johnson's algorithm, longest path problem, notes. References, Dijkstra, EWA note on two problems in connection with graphs. Numérique mathématique 1, 269 €271 doi, 10.1007/BF0138639 Corman, Thomas H. Lesserson, Charles E. Revest, Ronald L. Stein, Clifford. Section 24.3 Dijkstra's algorithm. Introduction to Algorithms. MIT Press and McGraw Hill PPA 595 601. ISBN A0-262-03293-7 Fredman, Michael Lawrence. Tarjan, Robert E. Fibonacci heaps and their uses in improved network optimization algorithms. 25th Annual Symposium on Foundations of Computer Science. IEEE. PPA 338 €346 doi, 10.1109/SFCS. 1984.715934 Fredman, Michael Lawrence. Tarjan, Robert E. Fibonacci heaps and their uses in improved network optimization algorithms. Journal of the Association for Computing Machinery 34, 596 €615 doi, 10.1145/28869.28874 Zinn, F. Benjamin. Noon, Charles E. Shortest Path Algorithms, an Evaluation Using Railroad Networks. Transportation Science 32, 65 €73 doi, 10.1287/TRSC 32.1.65 Lazorek, M. Gray, R.S. Johnson, A.A. Ladue, W.C. Meeker, J.R., S.R. Pittry, R.M. Seeds, R.N. Investigation of Model Techniques First Annual Report June 6, 1956 July 1, 1957 A Study of Model Techniques for Communication Systems. Cleveland, Ohio, Case Institute of Technology Newth, D.E. A Generalization of Dijkstra's Algorithm. Information Processing Letters 6, 1 5 doi, 10.1016/0020-0190, 77, 90002-3 External links, C++, Dijkstra's algorithm in C programming language, Dijkstra's algorithm in C++, implementation in Boost C++ library. Java, applet by Carla Lafra of Pace University, a Java library for path-finding with Dijkstra's algorithm and example applet, Dijkstra's algorithm applet. Dijkstra's algorithm is bidirectional version in Java, Hipster, an open-source Java library for heuristic search with Dijkstra's algorithm and examples, open-source Java graph package with implementation of Dijkstra's algorithm, Shortest path problem, Dijkstra's algorithm, visualization of Dijkstra's algorithm. C/net, Dijkstra's algorithm in C, fast priority queue implementation of Dijkstra's algorithm in C, quick graph, graph data structures and algorithms for .NET. Dijkstra's algorithm simulation, oral history interview with Edsger Dijkstra, Charles Babbage Institute, University of Minnesota, Minneapolis. Animation of Dijkstra's algorithm, Haskell implementation of Dijkstra's algorithm on bonsai code, implementation in TSQL, a MATLAB program for Dijkstra's algorithm, step through Dijkstra's algorithm in an online JavaScript debugger.